Hello. Purpose of this video is going to be to walk through the solution to this electric field tutorial exercise. First page of this exercise has us sketch some electric fields qualitatively. So in this case, we have in the first case we have two positive charges. So what does that look like? This gives us a chance to exercise our rules for drawing electric fields. You're going to have field lines that point away from positive charges, right? And in between here, they're not going to be able to connect each other because they're both positive charges. So what you would see is that they would curve away from the charge. So something like this. Remember, these electric field diagrams are not particularly quantitative, but it gives us some idea of what the field looks like. And notice right in the middle, there'd be a spot exactly equidistant between those two charges where the electric field vectors would actually cancel, and so there would be no electric field in the middle. You can kind of see that if you imagine doing this again and just looking in the middle. You'd have an electric field from that one that's pointing this way, and an electric field from the right charge that would be pointing this way. And so what happens, you add those together, you get nothing in the middle. And so that's reflected in this cartoon by having no electric field lines exactly in between the charges. And that would be a point where there would be no net electric field. This second example has 4 charges. So this is a quadrupole configuration. What would this look like? Well, you'd have electric field lines pointing from the positive charges to the negative charges. As we, according to our rules, we know that those field lines can't cross. And as we flesh this out, we would add field lines. And remember, the field lines, the density of the lines gives you insight into kind of how strong the electric field is. So close to those charges, there's more field lines, which would indicate that the electric field is stronger as you get close to the charge, which kind of makes sense. So it looks something like this, as we add more field lines, there would be field lines that point away from the positive charges, field lines that point towards the negative charges, etc. There would be a spot for this one as well where right in the middle the electric field from all four of those charges cancel, and so there's no field lines exactly in the middle. This is just another example of practicing the sketching electric fields. You can expect to be able to do that basically for simple configurations of charge like this. The real core of this exercise, though, is the second part. And this is where we get into superposition of electric fields. That is, adding electric fields together. This is similar to what we did with Coulomb's law and adding electric forces together, except now we're working with the electric field for point charges. A little bit different quantity. So the configuration that we're going to look at is the dipole. We have it arranged vertically, and we want to look at what's happening to this point P it's on a line that's equally between the two charges, but not right between them. It's off to the side, along the x-axis here. So what does this look like? The first thing that we want to do is, without doing any math, determine the direction of the electric field at that point. And you'll notice, so what we're going to do is, if we sketch the electric field for the dipole, just like what we were doing on the first couple sections, we can use that kind of sketch to inform what the electric field is going to look like for our more quantitative exercise in a minute, where we actually add them together. So what would it look like? There would be a line that would go directly from the positive to the negative charge, and then in between them you'd have these curved lines as well. And what we can see is that we can use this to reason that the electric field would actually point down at point P. And So let's add that to our diagram. Actually, let me put this in, I'll put this in red just to distinguish it. And I would note too that you can reason this out in another way, which is if we think of the two charges, you have electric field. The electric field points away from the charge, right? So with this positive charge, there would be I'm just going to draw it again over here. This is point P. From Q1, you'd have an electric field that would point this way. From Q2, you would have an electric field that's going to be the same strength because it's the same distance away that would point like this. Now, if our drawing was really good, it would be very clear that the x components of that are going to cancel, but the y components are going to add. And so kind of the cartoon drawing it this way would show us that the net electric field would point down as well. So this is just another alternate way to think about it. So we can reason out the direction for E, the net electric field at point P. The next part has us examine the electric field expression for a point charge. So that's this guy. This should be familiar. We talked about this in class. And the thing that I want to draw your attention to is this unit vector, R1. So the cool thing about how we're going to do this problem is rather than using sines and cosines, trig functions, to extract the components of the electric field in x and y, we're going to actually use the unit vector to do it for us. And the cool thing about this is that if you use the unit vector, you don't actually have to use trig at all. And if you're not using trig, there's no worry about getting those components swapped around if you're not using your trig functions. You can't, in other words, you can't, mistake sines and cosines when you're not using any sines and cosines. So in order to use the unit vector, we have to rely on the definition of what the unit vector is. And so the first thing that we're going to do is actually explicitly draw the vector R1 and R2 on our diagram. And so what does that look like? Well, what is R1? R1 is the vector that points from Q1 to P. So R1 looks like this. And likewise, R2 would be the vector that would point from Q2 to P. So those are the vectors R1 and R2. And now we're going to make use of the definition of the unit vector to figure out the components. So what are the x and y components of R1? Let me just sketch this again so we have it right in front of us. But what does it look like? Well, we had R1 looked like this. And if we look back at the diagram, we would see this is 5 centimeters, this is 12 centimeters. And so the x and y components of R1 are just explicitly 5 centimeters in the negative y direction, 12 centimeters in the x direction. So what does that look like in terms of I hat and j hat? We'd have 12 centimeters in I hat plus 5 centimeters in. I'm going to keep the sign with the unit vector. It doesn't matter. You could write it, just as well write it like this. But just to indicate that in other words, it's pointing down, the y component. So that's R1. And then use the Pythagorean theorem to find the magnitude. We can find the magnitude of R1. It's just a triangle, right? So the magnitude of R1 is square root of x squared plus y squared. You'll notice these numbers are picked so that this is convenient. The square root of 5 squared plus 12 squared gives us a nice round or a nice whole number, 13. So R1 hat equals R1 over the magnitude of R1. Let's put the pieces together. And this is the unit vector r1 hat in terms of our familiar unit vectors I hat and j hat. And now we can use this by basically putting it into our expression for the electric field. So let's do that next. So next we want to figure out the components of E1. Well, what is it? It's E1, the vector. Just substitute this in. Now this thing is in terms of I hat and j hat instead of being in terms of the unit vector r1 hat. And we could put in our actual numerical values because we know the charge. So let me do that quick. It's 12 nanocoulombs. We got to put this in meters instead of centimeters so that our units work out. And if we crunch those numbers, we would find that this is this. Okay. And we could multiply through the to get our two components we want. It's basically the same thing, but just to have numerical values for both, what would we get? We get 5.9 times 10 to the third newtons per coulomb in I hat minus 2.5 times 10 to the third newtons per coulomb in j hat. So no trig functions, but we've extracted the x and y components of E1. So what's our next order of business? We do the same thing except for E2. What does E2 look like? It's going to look almost exactly the same, except E2, remember, was pointing like this. E2. And basically, there's two differences. The charge, so Q2, is negative, and there's also the other difference is that the direction, the x, the directions are also are different. There's a sign difference. So let me lay it out to you. So this will be very similar. So what is R2? Sorry, this is R2. R2 is going to be 5j plus 12i. In other words, both components are different. So that's the difference in the vector R2 compared to R1. But also the sign is different. So how does that manifest? Well, when we put those ingredients together, E2 is going to be the same magnitude, except Q is negative instead of positive. In other words, I'm just putting in the fact that Q2 is negative Q1. And then I'll put in our unit vector, R2 hat. And if we multiply those things together, what would we find? We'd find that E2 is negative 5.9 times 10 to the third newtons per coulomb in I hat minus 6 times 10 to the third newtons per coulomb in j hat. So notice the x components, the I hat components, for E1 it was positive, for E2 it is negative. So that it just reflects what we saw above, the fact that one of these points like this, one of these points like that. So the x components cancel, but the y components are both negative. The y components are going to add. This is showing us that it's consistent with what we saw with our cartoon before we started doing the math. So what's our last step here? We want to add the x and y components together. Like we just said, the I hat components cancel. Here, I'll write it down explicitly just so you can see it, but that means that it's going to equal E1 plus E2 is going to equal what? 5.9 times 10 to the third minus and the other one, right, negative 5.9 these cancel out, and we're left with just one component, negative 4.9 times 10 to the third newtons per coulomb in J hat. So it's pointing down. And that's our result. That's the net electric field at P is that number. All right, so that's how you do it with the unit vector. And this is entirely consistent, though, with doing this using trig, using sines and cosines. So let me just show you real quick what that would look like. So the last bit here has you do this by using trig. So just if this is more familiar with you, hopefully this kind of more familiar to you, hopefully this kind of brings things together. So in order to do it with our trig functions, first thing that we would do is find the magnitude. So the magnitudes of these are the same, right? E1 equals magnitude of E1 and E2 is the same because the magnitudes of the charges are the same and the distances are the same. So what does that look like? Well, that's 1 over 4 pi epsilon naught Q over R squared. If we put in our numerical values, we had 12 nanocoulombs, 0.13 squared, 6.38 times 10 to the third newtons per coulomb. Second part, we need to use our trig functions to find the x and y components in terms of theta. So actually, let me sketch this again. So we had Q1, Q2, this point P. So we got to kind of suss out what the functions would be. Here, this will be sufficient. So for example, if we were, let me put this in red. If we were looking at E1, E1x would be here. E1y would be here. So we could define theta like this. It's probably the most convenient place to put it. And so that would mean what? That E1x would be E cosine theta. Okay. And likewise, E1y, E sine theta. And actually this would be, this would be negative. And we could, we would follow the same reasoning. The cosine pieces we're going to see would cancel. The sine pieces would add. So what does that mean? Well, our E net then would be negative. It's going to be negative 2 because there are two components that are adding together that are the same, times the magnitude times sine theta. And what does that look like? It'd be negative 2. We can put in our magnitude, our expression for the magnitude, times sine theta. What is sine theta? Well, sine theta is the opposite over the hypotenuse, right, according to our definition. What is that? Well, the opposite was the y component, the 5. The hypotenuse is the 13, so this would be 5 over 13. You see how this is exactly what we had up above. We put that in, negative 2, times this magnitude, 6.38 10 to the third, times our 5 over 13. What do we get? Same as above. This would give us, the same thing that we saw above, the negative 4.9. 10 to the third. And what is that? That's in the j hat, y direction. Moral of the story with this is, as it should be, the same result that we got with the unit vector approach, but using trig functions. I don't care what approach you use. I just want you to have as many tools at your disposal as possible, and so that's why I'm showing you that, showing you this both ways. So hopefully this is helpful as you're working on learning how to add electric field vectors.